So let's wait for 2-3 more minutes. Let's see how many else join. So then we will start. Okay. Okay, so let's start. So hello everyone, my name is Raja Mukherjee and I will be taking this tutorial for NPTEL course on reinforcement learning. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So like always, we will be solving some tutorial questions like those that are asked in your assignments or your end exam. And as well as we will discuss whatever was on a brief, whatever was taught in this week's course in this week's lecture. Feel free to ask any question if you have any whenever you want. And this video session is being recorded, so you can access it later. Okay, so let's start. So this week we came across first the term policy. So last week we are discussing the last 2 weeks we are discussing bandit problems. So what was there in bandit problems? So you have few arms and there is an environment. You pull one arm at one at a time or one at one time, and you so pulling the arm is your action, and the environment gives back you some rewards, right? Some rewards it gives back to you after the action, for every action, right? So our goal was to maximize the reward, right? And the things which we discussed in doing this were some algorithms like greedy algorithms, like normal greedy algorithm, epsilon greedy algorithm, UCB, those kind of concepts we learned and saw how the effects of these bandit problems can be changed with respect to some epsilon values, some upper confidence bound values, some initial values changes. So also we went through not only a stationary object through a non-stationary object, these concepts we talked about. Now now we come from this for this week we come across the term called policy. So what do you mean by a policy? So policy is defined by your this pi. So policy is defined by pi, and policy is dependent on a action. So what does this means? This means for some so for some value for some action A there is a policy pi. So in case of like bandit problems, this basically is actually the probability of selecting arm I, right? So that is probability of selecting arm A. So that is basically PR arm is equal to A. Sorry, uh, AT AT is equals to A, right? So we also went a little bit different. Uh, so in bandit problems, in so far those bandit problems, so how which arm were you basically selecting? Which arm you are basically selecting? You are selecting the arms which has given us more rewards in the future, in the past, right? We are selecting those arms, uh, thinking that they will also give us great values in the future, right? In this problem, we say that we will not select like that. We will have some particular parameters based on which we will select the arm, and those parameters are not basically your rewards. Those are something else, which can be anything. So this probability is given by uh, it's given by e to the power of HTA summation of A e to the power of HT B. B is equal to 1 to K. So suppose there are K arms, right? So now we are saying that we are selecting not on based of value, we are selecting arms not on based of value but some other parameter HT, right? So this denotes that now we are not selecting it based on values, but we are selecting on some different parameters which are denoted by e to the power of HT of A divided by the sum of all the arms. So this is for a particular arm A, the top, and the denominator is basically the sum of all the parameters. Okay, clear? So the main difference previously our goal was to select arm based on what we have seen before, the rewards we have seen before, but here it is not. Here we are given some particular stationary uh, parameters, and based on which arm satisfies that parameter more, we select that, and that is basically a probability distribution, right? So now how do you update the reward? So in previously you have seen how do you are updating the rewards. How we are updating the rewards? We are updating the rewards as uh, qt plus 1, well, like is equals to qt plus alpha rt minus qt, right? Using this formula we are previously updating the values. Now what we are doing, we are learning these parameters. So this ht parameter we are learning. Okay. So this ht parameters learnability has been defined by some particular equations. So let me share this screen. Uh, Here I have written down the equation. So this is your equations based on which we are updating it. So ht plus 1 is basically HTAT into some step size into this reward difference, and this is your update rule, right? So this is the case, this is the case when you are selecting an arm AT, like a particular A, and this is I'm updating its parameters, and this is for the rest of the case for the particular A. When we are not selecting that arm, we are updating it. Okay, so this is all. So in the class you have come across this portion as binary mandate, right? So binary mandate problem was kind of like this. So either if you take the if you pull the arm, you are getting 1 as a reward, else you are getting 0 as a reward. So these equations are quite similar to it, right? Now here you will find two terms. One is RT, another is RT to the power like RT dash, right? So what is the difference? What is RT and what is RT dash? So your RT is basically the reward you are getting at timestamp t, and RT dash is basically the baseline reward or the average reward that you have received in the back, like previously. You are doing a like subtraction of that, and that is the updated extra RT you have got, right? So what if you get an RT0? What will happen? What if I get an RT0, RT dash 0, sorry, the baseline as 0, RT dash is called baseline reward. So if you get that as 0, what will happen? What will happen if RT dash is 0? No rewards. Yeah, we will check it with the graph. Okay, so so one thing. So if the difference between RT and RT dash is 0, what will happen? Then we are updating the parameters in a rapid way. So one more thing. So if you look at this equation, it is quite similar to your normal machine learning problems where you have seen a thing which is called stochastic gradient descent, right? So this equation is quite similar to your stochastic gradient descent equation, right? But there is a difference. So in gradient descent, what you are doing actually, so if you remember your ML class and all, what happens in gradient descent? In gradient descent, so after a forward pass, you get some output, and you compute what is the difference between the output that you have generated and the output and the output that is the actual output. So you do a subtraction of that, and that is the portion of your error, and what you do, you update your parameters based on that error, right? So that is your stochastic gradient. So in that case, the what your like you are always getting an error, either is a positive or negative, and you what your task is to minimize the error, right? Here our objective is different. Here our objective is to maximize the reward. So there your concept was of minimization, here the concept is of maximization. So in stochastic gradient descent, so it will always, our task is to minimize it, so as close to 0 it is possible. Here our task is not that, our task is to maximize the reward as much as possible, right? So if RT is taken, RT dash is taken as to be 0, so if the RT value is, so if RT is greater than RT bar, then what you have is you are getting closer to you are reaching your ascent, doing the ascent much faster, right? So now let's look at the graph and see what is the effect if the baseline is 0 or not, right? So this is your graph. So in this case, you have step size. So sorry, so there are two step size, 0.1 and 0.4. Okay, so yeah, so these green and red are your 0.1. Okay, and this one is your baseline is false, and this is baseline is true. So you can see the significant optimal action we are taking when our baseline is present, right? When the baseline is present, we are getting a significantly higher optimal reward compared to when baseline is not present, right? So this is a sample code which I have taken, and it's not much difference. The code is quite simple like previously. So here, what I can show you where I am doing the equations, here is your equations, the two equations. So here we are calculating 80 plus 1, right? So this is your equation. Step size, mean reward, and this you when you are taking the action. How does does it turn out to be a better than UFC or epsilon UFC, not UCB, sorry, not USB, UCB. So does this turn out to be better than UCB? No. I have that graph that is there in the book to show the which one is better and which one is not. Let me see if I get that graph or not. Give me a second, I will load it. So, any more questions regarding this, or I will else move to MDP? Yeah. So one more thing. So in the lectures, they were shown much more in depth of this policy and all, policy gradient search, reinforce. Uh, so you can go through the lectures and do it. So the rest, a few we will go when we are going through the exercises. We will solve some problems there. We will discuss in details. The rest. This is just an overview of what was there. Okay. Uh, we will go through it then. After this, we will go through the MDPs and just discuss basic what is MDP and all. No, MDP is part of week 3. The lectures, lectures 4 and 5 of this week are MDPs. There are 5 lectures, right? So first one was your uh, like this gradient, policy gradient and all. Second one was your reinforce. Third one was contextual mandate. Okay, I will come to contextual mandate and then the MDPs. So is my screen visible? Yeah. So this is a kind of a diagram of the what we are trying to show there. So this is the average reward over 1,000 steps. So this is your alpha greedy. alpha greedy, this is your gradient bandwidth, this is your UCB, and this is your greedy with optimistic initialization. So this gives a comparison uh, of your which one is better than what. Right. So, I will again say that read the book. The book is very nice book. Like it is not very high level book. It's the beginning chapters are quite easy to read and all. Okay, so let's come back to the slides. Book seems easier lecture. Yeah, I mean that's kind of true because I will not say it's true because what the week two's problem was those were taken directly from your some research papers. Okay, and the bounding was a little bit tough to understand. I mean, you are not also given the whole research paper. It was like 10% or 20% of the lecture research papers. So the proofs were a little bit difficult to understand there. Good thing is the book is freely available. Okay, so let's come back to contextual bandit. So, so this is the last step of your bandit lectures. So, so what you are still doing as of now, we are just selecting a arms. We have few arms and an environment, and we are pulling some of the arms and getting the rewards from it. Right. So this was our bandit setup. Now consider a case where suppose this one is T1, T2, T3 and T4. Suppose I use T1, and when I get suppose here there is some kind of colors. Okay, so when you pull it you get some reward as well as some color to it. Okay, so reward plus color. So you check that whenever you are getting a green when pulling T1, you are getting a higher reward than suppose you are getting a color red, then you are getting a lower reward while pulling T1. Similarly, same concepts are there for T2, like T2 the red is given more or pink is giving less, so kind of things. Okay, so as a sir, the link from the book is not available in 7th. Just go and search. Oh, I am giving you the link only. Okay. So it's a free book. So you have, so you're pulling T1, and if you see a green color on your environment, so you notice that you have a higher reward than when you're getting a red color, you are getting a lower reward. Similarly for T2, suppose you have getting red, you are getting a higher reward than when you are experiencing a screen pink, you are getting a lower reward. Okay, so so gradually you come to an understanding that okay, so if I pull T1 and if I get green, I will get a bigger reward, right? So you are getting some context along with your reward, right? So that is why it is called contextual bandit. So this is called this could be called a 3/4 of your MDP problem. So later we will come to an MDP problem, but previously while you were only focused on your action, Now action and reward, now you are getting something else, you are getting also something called a context to it. So that is your contextual bandit. So once I discuss your with you the other problem, the MDP, so you will be much more assured that what why contextual bandit is just a first step towards your MDP, right? So let's come to the MDP. Okay, so let's look at part of decision process. So now we are introducing you to the full reinforcement learning problem. So you have an agent and an environment. So the cycle goes that is, the first somehow the agent senses what is the state the environment in is. Suppose it is currently in state S2. Okay, so accordingly to it, it sends an action AT, right? According to it, it sends an action AT. Now corresponding to this action and a state ST, it gets a reward RT, and based on this action the state changes from ST to ST plus 1. Now changes to ST plus 1, right? uh, just for context, so after receiving 80, it should get 80 plus 1, but I'm just RT plus 1, but I'm just assuming that previously there was no reward, but in most cases there is reward. Okay, so let's so if we look at the state diagram based on this, it would be something like this. So previously you are on state S0, you take action A0, right, based on it. Now you get reward R1 due to it, and you move to state S1, right? So this is happened. So initially you was an S0, you get action A0, you get a reward corresponding to it R1, and state changes from to S1. So that is your state transition from one state to another. So S0 to S1 you will get this. So if you like it like this, it will be something like this: S0, action A0, reward R1, state S1, right? So this is how you denote it. So similarly it will be action A1, state R2, reward R2, and state S2, right? This is how you denote your MDPs. Okay, now what is a policy? So let's not look into the policy first. So let's now look at into this term, probability of S star R given S comma A. What does this probability mean? This term indicates that at state A, so you are at a state S and you have taken action A. What is the probability that the reward will be R and the next state will be S star, S dash? So basically you are saying, so you are currently here. What is the probability that you will get this after applying this to the environment? in this environment and action pair, what is the probability you will get this, right? So this is your probability. So this is the probability it denotes. So if I write it, so is the probability probability s of t is equals to s dash comma r t is equals to r given s t minus 1 equals to s a t minus 1 is equal to a, right? This is your probability, right? Now you want to find out, so now you want to find out this probability of being in state s given you are in state s comma a. Suppose you want to find this. So what does this indicate? This indicate that you are currently in state s and a. What is the probability you reach state s dash, right? So it is basically a summation of this all, right? S dash r comma s of a given r belongs to r, right? For all the rewards you need to sum it up, right? That is it. So this is your 1 2. Now number 3 is r of s comma a. So what is the total reward at this, at state s comma a? What is the reward you are getting for action a given state of s, right? So first so again I will come back to this one. So what we are seeing is in equation 1 was this whole system. Now equation 2, what we are trying to say is this. So given I am at, so what is the probability I will be at state s1 given I have been given this and this, right? So what we have to do, we have to sum it over all the rewards due to which for this pair, right? Now similarly I am saying that what is the reward. So now I am trying to find out what is the reward, what is this reward if I have been given s and a0. So it is given by this equation, an estimate of it is given by the estimate of RT given s of t minus 1 is equal to s, comma a t minus 1 equals to a, which on turn is basically sum of r belongs to r multiplied by p of s dash r comma s of a, right? So we are summing it over for s dash belongs to s. So we are summing it over all the states. For this reward, for these two states, what is the total reward we are getting? We are summing it over all the states and all the rewards, right? Nothing much fancy. So we have to find this, and so we are summing it over all the states and this. Okay. Now Let me find another Jamboot. Okay. Now we are to we are trying to we will select check another term r of s a r star, sorry, a star. So what does this mean? So you have a you have given a particular state, you are at a particular state and you choose a particular action and you come to another state. What is the total reward? What is the total reward? So this will be given by summation r belongs to r, p of s comma r comma s comma a divided by p of s dash s comma a. Right. So we are saying that what is the total reward to reach from s a to s dash. Okay, so this is our fourth equation. So the first equation was giving us the total probability of being state A and R, S dash A and R, given S and A. The second equation give us what is the probability to be in state S dash given the initial state was S and A. Second one was what is the total reward we can expect from a state A and S, from a state S and action A. And the third one was given a state S, action A, and next state S dash, what is the total reward we are getting. So these are our four equations for the MDB. So what is our goal in an MDB? So the goal is maximize future reward. Right. Now let's come to what is a policy in this setup. Policy is basically a mapping of action. Probability is a so policy is a mapping of action sorry probability is policy is a mapping of states to action. So it is given by p of pi of a given s. Right. So this is the difference. So previously we are not taking into consideration the states. Now we are taking into consideration in the states. So in bandit, no states. But in a full reinforcement learning problem, there will be states. There will be states. Right. So this is your policy comes. Next we will come to a term called return. So return R, return G at state T is basically return of the future rewards. Right. This is what you mean by your return. So in the return at time t. So we are considering that this is a finite task. So t will be fixed. Right. So as an example, take a game of chess. So what is a game of chess? You there are two players. You move your pieces. You have your bishop. You have your knight. You have your pawns and all. So the initial state when both of all of you have both you and the opponent are at the same stage. The pieces are on the board, right? That is your initial stage. So suppose you are a white or you are or your opponent is a black. So your goal is to win the game. What is your goal? Ultimately to win the game, right? So your return in that case will be winning the game. Now suppose you are suppose at some particular state. So at a particular state you are at. So you wanted to know so whether you are winning or not at that case. So that case you can assume that a chess game of chess will eventually end. So either it will end you are in as a win, as a loss or a draw. So the RT, so the term T uh, will be fixed. So these things are called your episodic task. These are called episodic task because there is a finite end to this problem. All problems don't have a finite end. So suppose you have a robot whose task is to pick up cans. Okay, so it has only one task of picking up a can. So in that case, it is a non-finite task because it will always take a arm and pick up the can and put it in a dustbin, or it will recharge. So after some time, if the battery drains out. So these are your states, but there it will never stop, it will always work. But in a game of chess you will always stop. So let's consider a game of chess. So the return in that case will be return in at one state t will be sum of all the future rewards. Now your question will be how can we guess the future rewards? That's the challenge. So because based on this return estimate, you will select the one with the best action. So you will pay the game of chess. You will move that in a game of chess. You will move that piece, which will give you the future best return, right? So think about it. Okay. Now you are also introduced to this term GT is equal to RT plus gamma RT plus 1 plus gamma square RT plus 2 plus dot 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 gamma T minus 1 RT, right? So this one was your discounting factor, right? So what does this mean? So let's consider the value gamma is equal to 0. So in that case the goal will be to have maximum return, i.e. the one. So we will always, our goal will be our maximizing the nearest return, maximizing nearest return. So again let's consider a game of chess. So you are have some position after, let's say after 30 moves you have some position. Okay, so you have two options. So one possible move can be your moving capturing a knight. So you have a knight, so there is a pawn, you have a knight and you have a bishop. So using this knight you can either capture a pawn or you can capture a bishop, right? So maximizing the nearest return will be that, okay, the bishop has a more value than pawn, so let me capture the bishop. Okay, that might not be is GT is respect to the GT is this GT is with respect to the action taken at time t only, right? Yeah. So at time t, what is the maximum reward we are getting? So we'll come to that. So we'll how this is related to your action and all. We'll come to that later. In next word only we'll come back to it. How GT is related. So what I'm saying is that So in that case, it will be our task will be the maximum the recent reward. So our recent reward will say that okay, capturing the bishop will give me more value. So let's capture it. The other thought will be capturing the pawn will give me less reward. So let's not do that. So that is your maximum the nearest return. But it may be that capturing the pawn would have been a better option. I believe GT is not an action. No, GT is not an action. GT is the return. GT is return. Action is different. GT is written in the sense that what is the future reward you are getting. Yeah. So as I'm saying, so in a game of chess, this is there. So it may be future down the line. You may find that capturing the pawn would have been a better option because that would have given you a better chance to win the game, right? So as a result, this discounting factor is there. So discounting factor, by adjusting this discounting factor parameter, you can say how much is the future return will maximize your current, will motivate to take your current action. So at the end of the day, our goal is to take the action which will give us maximum the GT value. So goal is to select the action which will give you the maximum GT. Right. So so the discounting factor keeps a balance of which to prioritize more, the future or the current. Right. So that is your GT. Basically, sum of all the future rewards is GT. Okay. So let's look at now value function. So so we discussed pi, right? Pi of s given t is basically the policy. So given a state s, what is the action I am taking? Given state is, what action I will take. So suppose this is a deterministic policy. Deterministic policy means this policy will be same for all kinds of action. So there is only one pi. So deterministic policy. So v of p, value of pi at state s, is basically given as what is the expected GT given pi at state st at s, right? So this is your what is the expected value you are getting at state s. Okay, so I will give you an example, very nice example. Okay. Let me open it. Yeah. So you can view the board, right? So this is a state of the game, okay, of this chess game. So this is your state of the chess game. So you can see the bar, right? There is a bar, this bar, and it is giving a value +7. So this shows, so this is your value function. This +7 is basically your value function. So this shows that given at this state, the probability of like there is a high chance of your white winning, right? So that it basically shows. So that is what v by s means. That is what your v by s means. So this +7 is your value function, and it's showing that given at this 8s, I will get I have a very nice chance of winning the game. Now let's come back to this. So now there is another term called q function. What does it mean? Q of pi given s comma a. So given a state s, we are a state s, and means we are at state is what is the return if I choose action A. So that is your given by gt s comma st is equal to s, at is equals to a, right? So so if I have to, if you think about it practically, it is something like this. So suppose I have this I have this queen here. So if I move the queen, if I move the queen, what is the value I am getting? So here it says, so if I move the queen, what is the value I will get? So right, let me draw a few back. So here, if I move this rook, if I move this rook, what is the value I am getting? So that is what it means, right? So that is how you state the action. So your movement is basically moving the rook to capture that piece, another rook. So that is your action, and what is the return you are getting based on that? So that is your value function, a function, q function, right? So that is given by this. Given at state A, if I take action A, what is the return I am getting? Right. So any doubt regarding this? So this was the part of the lecture that was discussed this week. So any doubt regarding this GT, V pi, Q pi, anything? Okay, so let's go to the next one. So let's start now solving some problems. Okay. So which of the following is true for MDP? So let's look at each of the equations one by one and try to solve it. So what does this state? What does this mean? What does option A mean? So this option A means option A means that probability of being of being so probability of being in state st plus 1 and reward rt plus 1 given st and at is equal to probability of state st plus 1 comma rt plus 1. This is what it is trying to show. Is this one correct? No. Why? what does this mean? This actually if this equation basically says that getting a reward rt plus 1 and going to state st plus 1 is independent of previous states. This is what it means. This is what it is trying to portray. And that is not MDP. MDP clearly states that uh, next state and reward depends on the previous state, right? So this one is wrong. So this one is not true. So this equation is trying to say that is the events st plus 1 and rt plus 1 are independent of the previous state and action, even the previous state and action, which is not correct. So A is false. A is false. Yeah, so correct. So it is not correct because it is trying to show that the next state and the reward is independent of the action and the previous state. So that is not correct. That is not what MDP says. Next one states that the probability of the state being in R1 ST1 given the previous state and action were this is equal to probability of ST1 plus 1 and RT1 plus 1 STN. So in short, this actually means this what this equality trying to show that the next state and reward is only dependent on previous action and state, and history is not required. This is what this statement trying to show. Yes, it is correct. So Nikhil is correct that yes. So this equation is correct because this Markov problem is like that. Markov assumption is like that. That to go to the next state, you only need the information of the previous state because the previous state is a culmination of the entire history. So ST actually knows all the history previous that. So you don't have to mention it back to ST plus 1 that what I have done previously because ST already stores that information to itself. The state ST is resemblance of that. So this equation is correct. So next state and the reward is not dependent on the entire history. It only is dependent on the previous state and the previous action. Right. So this one is true. Now let's come to option C. What does this mean? PR, so probability that ST plus 1 and RT plus 1 given ST and AT is equal to the probability of ST plus 1 RT plus 1 given S0 A0. So this is trying to say that the next state and the reward, the T plus 1 state and the reward is dependent on ST and AT, and ST and AT and A0 and A0 are same. So it means to say that state S is equivalent to initial state and AT, that is action at time t is equivalent to initial action. And this is not correct, right? It is not correct. We all know that it only depends on the previous state and not the initial state. These two states are not same. These two states and these two action pair are not same. So this is false. Now let's come to option D. So if you have understood the 3 points, then you should know what is this, true or false. You should by now know that if it is what it will be. No, it is t minus 1. Why the probability of choosing of being in state st plus 1 and rt 1 will be same as that of st and st plus 1? It will not be same. Yeah, but we are not considering stateless bandit, right? What do you mean by stateless bandit? A bandit is stateless. A bandit doesn't have a state. Bandit doesn't have a state. Bandit only have action. And this is an MDP. So MDP does have state. Right. So this one is also false. Because these two probabilities will not be same. Will be different. What is the probability of me selecting the state? Why? What has to deal with this probability of selecting the TF state? It is completely different. Okay. So option B is correct. Any doubt regarding this? Okay, so let's go to the next one. So in the baseline in the reinforced update should not depend on which of the following. Okay, so what was the baseline? So what was our reinforced update? ht plus 1 at action taken at time t is equal to ht of at plus alpha rt minus rt prime 1 minus pi of at at. Right, so rt dash is baseline, right? So what is rt dash? Rt dash is basically the average is the mean reward which you have witnessed previously, right? According to the gradient bandit algorithm, gradient policy search, right? So it depends on both Rn minus 1 and Rn, right? It needs to find the mean. So it is dependent on Rn dash is dependent on Rn and Rn minus 1. But is it dependent on action taken in? No, it is not dependent, because these are estimates of reward. Lecture the professor says that it should not be dependent on action in, but does not give the reason. Can you state why? So it will not depend on rational error. It is a summation of all the rewards we have seen so far, right? So you take the action and you go from you get the reward rt plus 1. So you get rt plus 1 how? By taking action in.
No, in the in the video it mentions that one of the choices of the baseline is the average reward,
Yeah.
right? right? There could be other choices. As long as the choice doesn't depend on n, you are good.
Yeah,
So it doesn't mention why the choice should not depend on n.
yeah, because
So
AN is your latest year. So AN is the action you are taking, right, at step N. But RT and RN and R minus 1 you have already witnessed. So when you are taking an action N, so when you are taking an action N, what you are getting? You are getting the reward Rn plus 1, Rn plus 1, right? So Rn plus 1 has no, so Rn plus 1 is the future reward. So it is not the reward which you have taken previously. It doesn't affect the mean, right? Mean is up to n, 1 plus 2 dot 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 up to n. So mean is up to n. So it should not, it should not be part, Rn minus Rn plus 1 is not part of it, right?
makes sense. So indirectly is saying that it should not depend on Rn plus one.
Yes, because it is the future.
Makes sense. That makes sense.
So yeah, so that's all the explanation. Okay, so reinforce update should not depend on action an plus 1. Okay, so let's go to the next one. So in many supervised learning algorithms such as neural network, we depend on gradient descent technique, right? However, in the policy gradient approach to bandit problems, we made use of gradient ascent. This discrepancy mainly attributed to the difference in objective of learning parameters, the parameters of the function where gradient are being calculated, the nature of the feedback received by the algorithms. Fine, fine. So here you have your email and here you have an RL. So here you have gradient descent and here you have your gradient ascent, right? So in ML, your objective is, what is your objective? Your objective is minimize error. In RL, your objective is maximize reward. Obviously, what will descent do? Descent will try to minimize it, bring the error to 0, bring error to 0, right? And here get me max reward. So the objective and the feedback are both different, like, so here the objective is to minimize error, so we are getting an error, here we are getting a reward, so our objective is to maximize the reward, right? So the option that will be correct is option A and C. So any doubt regarding this you can ask. Okay, so let's go to the next one. Okay, so this is little precocious to say, so let me just it didn't fit in the slide, but let me just say it again. So you have been given a case of linear bandit and there are two actions, A1 and A2. Is it visible? Okay, okay, So try to go to this link. 1 minute. Yeah, so if you can go to this link, you can get the problem. It is little bit difficult to see. So what it shows is that we have two actions, A1 and A2, and we have a policy pi. We have a policy pi for we have two actions A1 and A2 and policy pi, and we have a state S. We have a state S. So when uh, where W1 and W2 are two weight vectors associated with A1 and A2, if you are using reinforce to learn the parameters, what will be the update for W1 and W2? So, so what we have to find basically is um, the update rule. So basically, this update rule we have to derive for this these policies. Okay, so let me write it down here and then we will do. So you have two policies, one policy, sorry, pi a1 of s e w1 ts divided by e w1 ts plus e w2 transpose s. Right, we have to find the update rule for let me show this time. Yeah. So we have to find goal, find update rule for w1 and w2. So let's now look at the formula of this. So the normal update route will be w1 is equals to, so this part will be remain same, right? These parts will remain same. This part of the code will, of the update will part will remain same, right? W1 is equals to W1 is equals to W1 plus your step size alpha alpha, your reward R, and some constant here. Similarly, W2 is equals to W2 plus alpha R, some constant, right? So what is this term that is to be given here? What is the term that is to be given here? So according to the reinforced algorithm, so it should be mm, derivative of ln ln pi ln pi a1 by s ln pi w1. Right. So this is the update that it will be. So if you remember the one that actually is the formula theta n ln by theta n pi theta pi an by theta. So while an is the nth action and theta n is the corresponding parameter. So similarly y2 will have some similar expression. So it will be wn pi a2 by s divided by ln of w2. Right. So let's look at the first expression, this one. So we will consider this expression first and try to solve it. So the expression is ln of ln pi a1 by s divided by ln of w1 divided by r derivative of w. So we need to solve it. So what was w1 pi of a1 is, what is the pi of a1 is this value. So this is the value we will substitute there. So this is the value we will substitute in place of that. So we will write it down as lambda ln w1 e to the power of w1 transpose of s divided by e to the power w1 is w1 transpose of s plus e to the power w1 w2 transpose of s equal to, so if you, since it is ln, we'll break it down like this. So since it is log division, so what is this? So if is log a divided b, we can write it as log of a minus log of b, right? So similarly we will write it down here same. So ln of e to the power of w1 transpose s minus ln of e to the power w1 transpose s plus e to the power w2 transpose s, right? We can write it like this. Now this will become ln and e, it will cancel out, so it will become e to the power w1 w1 transpose s minus this term, right? ln e to the power w1 transpose s plus e to the power w2 transpose s, right? Now if I do a derivative of this, it will come out to, since this w1 s, so it will become w1. So this is basically derivation of 10x by d of x is equals to 10, right? So this w1 will come out minus, so not w1 will come out, s will come out, s will come out minus whole of this w by w1 e to the power w1 ln s plus e to the power w2 ts. Now, so what is the derivation of, let me just take it as a rough one. What is the derivation of log of x by dx? It is 1 by x, right? So we will apply the same chain rule here, s minus, so this ln part will come down, e to the power w1t plus e to the power w2 ts, and what it will be above. So this is derivation of whole this. Now we have to derivate this part, right? So this will come out to be, so this will come out to be e to the power w1 t transpose s into s, because after that we will equate this part, right, through chain rule. So this is the final one we are getting. So let me use a different ink. So this is the final expression we are getting for it. Right. So from here, so these equations come down to this. Right. So now if you substitute it here, we will get the answer. So we will substitute this part here, which is s minus s minus e to the power of w transpose w1 transpose s divided by e to the power w1 transpose s plus e to the power w2 transpose s into s, right? So this is the expression we will substitute it here. So if we come back to our this one, to the original problem, this is your option number 1. So this is your option number 1. w1 is equal to w1 plus alpha r s minus e to the power 1 ts plus this and this. Okay, so first tell me if you have any doubt regarding this derivation for w1. I know it is a little bit big derivation, but at the end of the day, it is all derivatives. So any doubt you can ask regarding this. These are all the steps which we took. So any state, any doubt, like these kind of problems are quite common, I know, and this arrives. Okay, so like if you now, what will be the update root of w2? What will the update rule of W2? So we need to do the same derivations again, right? We will do the same derivations again. So let's start doing it.
So by symmetry, just the W2 transpose S will change. Nothing
Will it
special
be?
about that. Yeah, there's nothing special about it. It's
Yeah,
just symmetry.
but you need to remember one thing. We choose action A1.
Okay, makes sense.
We choose action A1. That is the difference.
Full action. Makes sense.
So if we choose action A1, what will be the different here? So you will have ln lambda W2 pi A1 by W2. A2 by W2, sorry. So similarly we will do the same one here. So let let me get the result we are getting here. Okay, s minus, so if you are using the same part, it will be s minus into the power w 2t s e to the power w1 t t transpose s t transport s plus e to the power w t transport s. Great, this should we be getting. But what is the difference we for the states we are not updating it? For non for e not equals to uh, w, since we are not selecting it will have different reward and state. Yeah, it will have different reward and state. It will have different reward and state. That is not that is not a problem. Oh, sorry. Yeah. That is my mistake. Oh, that is my mistake. Sorry. Yeah. Sorry. Yeah. Correct. What you have here said is correct. Yeah. So, what I was doing wrong, I will also say. So basically, it will be pi of a1 pi of a1 given w2 divided by w2. Yeah, correct. That is a2 will have different derivative state. Yes, correct. Because even though we are doing this, you need to remember that here we are selecting action a1. So action a1 with respect to s, sorry, will differentiate the same term. This is the mistake I made. So since we are selecting a1, so we will differentiate the same policy with respect to w2. With respect to w2, previous one we differentiated with with respect to w1, we will respect to w2. So for s1 only, a1 only. Okay, right. So let's differentiate this one. So we will have ln w2 pi of this one will become e to the power w1 transport s divided by e to the power w1 transport s plus e to the power w2 transport s. Similarly, we will again break it down because of this logarithmic. So log of a by b is equals to log of a minus log of b. So it will be w2 ln of e to the power w1 ts plus ln e to the power minus, sorry, will be minus e to the power w1 ts plus e to the power w2 ts. Right. Now notice this term. So if you do a derivative of this term, if you do a derivative of this term with respect to w2, it is a constant, so this term will become 0, right? Whereas, so at the end of the day, our choice will be to differentiate w2 ln e to the power w1 transpose s plus e to the power w2 transpose s, right? So this is the part which we will be doing. So this will come down to, so if we go back to this hour, so this will come down to this part. So it will come down to minus e to the power w 2. So first we will 1 by l, so 1 by l becomes this x, differentiation of ln x is basically 1 by x, so it will be e to the power w1 ts plus e to the power w2 ts, right? Now we will differentiate, this part will be constant, this part will be constant, so this part will be differentiated e to the power w2s. So log of differentiation of e is given by e to the power x is x, and this one will be the s. So the value will come down to this. So this value will basically come down to this, right? This is the update rule for selecting action 1 a1 at with respect to parameter w2, right? So here the correct answer will be number 4. You see, it has only one term. Can you explain with respect to the update formula you have shown earlier in your collab notebook? That will help us to intuition rather than, yeah. So let me go back to the collab notebook. So this is the part. So that is the part of the derivation is being shown. So if this this was some special, some special function was there for that, but here we are, in our case, so if you look at this diagram, so what is the difference here? So exponential of h t power, h to the power t power. Now we have been given a parameter with that. So our parameter in this case is now, in our case the parameter is this. So in our case the parameter is this one, w1 t to the power s. That is basically your ht, right? That is what we have done, nothing more. So here is your e to the power of h to the power ta, and that is basically this. That is basically your w1 ts. Now you got it. Okay, so let's look at the next one. So this is clear now. So this update formula and all, this is quite common question. So we still have to do differentiation of pi a1s with respect to a2. Yes, for updating a2, w2, yes. So that was the main mistake I made. So the update rule was for w1 and w2. There are two parameters, right? So here there are two parameters, w1 and w2. So the update rule of w2 with when we are taking action a has to be done. So that part I missed. A2 has different action. We don't have to think about A2 because we are now dealing with only W1 and like with only action A1 because it was picked. So for W2, yes, for differentiation of pi, A1 by S, but with respect to W2, that we need to do. Okay, so let's go to the next one. This took a quite a bit of time. Okay, so you have been given the update in reference reinforce is given by this plus this, right? This is the equation we just saw, where this is the unbiased estimator of the true gradient of performance function. However, another variant of reinforce, so this is the baseline variant. Now we are talking about the baseline variant that is independent of the action taken and is subtracted from the obtained reward, i.e. the update rule in that case is this. So how are this and this related? So how are this and this related? That is our question. So if you look at these two estimators, so if you look at these two estimators, there is one common term that is missing, that is b. So we will calculate this part, e to the power b into ln pi a t theta t by theta t. So we need to find the value of this part. Then only we can find the relation. So let's try out the derivation one by one. So if you do a ln of this part, what will it be? So derivative of this with respect to theta. So it will become e of b into, so derivative of d of dx log of x is equals to 1 by x, right? So we will apply the same chain rule, 1 by pi at comma theta ln of derivative of at comma t, right? So that is what you are trying to do. At comma theta derivative of pi at comma theta dA theta, right? So this is what this part comes. So now the estimate, so we can write it like this, right? So the estimate of this can be written at like this. So if you remember the estimate formula, what is the estimate formula? So estimate of RT is basically summation of x pi t x comma q star x, right? Summation of all the rewards and the policy, probability of that, right? So similarly it will be same here. You can write it down as summation of over all states a, since it was xa, so we can write it down as b into 1 by pi at comma t theta into this portion. So this entire will come down to this entire will come down to this. So at comma theta divided by a theta into this pi part, so that is will be pi at comma theta, the pi we have. So this one and this one will get cancelled, so it will come down to summation of a and the constant b into summation of at comma theta by a theta, right? Now if we sum up this all gradient, so if we sum up the gradient over all action, this will come down to a this will basically come down to, so if we sum all this, so uh, so let me delete some more problems and let me just delete few problems. Delete delete, yeah. So if we come here, so it will come down to uh, let's rewrite it again. So it will basically come down to summation of b, summation of b pi of derivative of theta t pi a comma theta t, and that is summation of our all actions, summation of our all actions. So now we can, so now if you sum up all the actions over t for a theta, so that will come down to a probability of 1. So if you know this, so over a theta t, so this will be 1, this will always be 1, because sum of action, all actions, sum of all action over a certain property will always be 1, because we are summing of all the actions, right? So this will come down to 1. So this will, if we sum out our all actions, this will come down to derivative of 1 with respect to theta t, so that will become basically 0, right? This is a constant. So at the end of the day, your this estimate, your this term will elevate to 0. What does that mean? That means estimation of this is equals to this 5, option A. Right, any doubt regarding this? So the concept actually, the only concept that is I guess will be a little bit confusing is how are you coming to this, right? This is the only confusion you will have, nothing more, because these are the terms that is quite common. This is derivative, right? Then uh, this converging this estimate to this form is similar. So you have your pi, we will multiply it over pi, and this is our estimate function, the estimation, this summation of all rewards. So here also summation we are doing of all rewards, so that part is compulsory. This we are cancelling it out, and only this portion remains. Now the only confusing part one is how we are getting this as 1, how we are getting this as 1. So yes, we are getting it as 1 because we are summing up all the, basically all the values. So if we sum up, so if I write it as step as this, So this value will always be 1 because you are summing up all the value of all the actions, all the probability of all the actions given are t, right? So that will always be 0, well, always be 1. Sum of all the probabilities always be 1. So that's the reason it will be 0, right? Okay, so let's continue to the next problem. So this is your let's say this is your policy search algorithm that you have been given in a multi-arm bandit, right? So this is your policy: pi t plus 1 is equal to pi t 1 minus alpha plus alpha this. Okay, so where I a of t a t is equals to 1 when we choose 1. So what does this mean? So this identity will be 1 only when we choose when a is equals to 80, value is 1, else 0, right? That what it means. And same is this same concept is this. So which of the following is true for the above algorithm? Is it a LRI algorithm? Is it a LR or like what is the, what LRI means? LRI means that we are adding the reward but 0 for plus reward, like for any positive work, like positive result for is reward, but for any suboptimal result we will choose 0, right? So that is what it says. Second one is we are adding r plus r for LR sigma pi sigma p. So but the our negative reward is less, like very small we are adjusting it. Third like, so if you look at this, this is not a LRI because we are not giving negative 0 for our non for our non selection of for the non reward. We are not giving it 0, we are giving it some values. And similarly it is not the reward is very high and the negative reward is small, that is also not the case. We are giving it completely same dimension values. Okay, so we are not giving it a small value. So this is basically a LR equals to P problem, that is reward and penalty are of same dimensions, not very hard. So if you look at option C, it says it would work well if the base term has a probability of 0.19 resulting in plus 1 reward, and the next base term has a probability of plus 1 reward. Okay, so probability of a optimal and suboptimal arm and the reward is same. There is no difference. So this is what it tries to define. The correct option is option C. I think this is alpha equal to beta similar. Yeah, correct. Alpha equal to beta, R equal to beta, not alpha beta. So it is reward is equal to penalty. R equals to P. Okay, so let's go to the next one. So the action in contextual bandwidth is not do not determine the next step, but typically do in a full RL problem. True or false? So as I said, contextual bandwidth don't do not have any state, do not have state. It just gives a it just gives a notion of it. Full RL problem has state, right? So this statement is true because contextual binary do not have the state thing. It just observes the state it, to get a maximum reward. It may observe the state to get a maximum reward, but it does not determine the next state. But a typical RL problem decides, because in RL you take a state, then a action, you get a reward next to it, and action state, you get a reward next to it and a state correspondingly. Right. Okay, so let's come to this one. So value function methods generalize well for continuous action when compared to policy gradient method. So what is the value action thing we saw? So let's go to our value action. One minute, why did I keep the value action? So, so in value action, what we are estimating, in a value action, we are trying to estimate the GT, right? So what is our GT? GT is the summation. So if this is a continuous action, the value of G will not be in bounded, will be unbounded. Like it will continuously goes on increasing, right? So so it doesn't generalize well for continuous function. It's true, but uh, for policy gradient it gives a much better option, because in policy gradient you are always selecting a action based on some parameters, and it doesn't matter if it is continuous or not, because the reward you are not accumulating continuously, because it is not dependent on accumulation. In policy gradient it completely depends on some policy determined by parameters theta and all. It doesn't much depend on the like the action that you are generated, right? So this one is false. Value function do not generalize. Okay, so let's go to the next one. So the next one says you have been given let us assume that for some full RL problem we are acting according to the policy pi. At some time t, we are in a state S where we do action A1. After few time steps at T1, the same state S was reached when we perform A2. Which of the following statement is true? Which of the following statement is true? So it says that you have a, so at time t you are at state S, and you took action A1. Now after few time steps t dash, you again reach step S, and where we perform A2 instead of A dash. So which of the following statement is correct? Is pi a stationary policy or a non-stationary policy? So this doesn't give us much idea whether a pi is a policy is a stationary or non-stationary policy. Correct? Because it doesn't mean that we have reached previously a state which have shown that it will just be the same. So it doesn't give us much idea of these statements that whether it is a stationary object or non-stationary object. So the correct answer is C. It doesn't give us much theoretical knowledge from this step. We cannot determine it. So let's go to the next one. In solving a multi-bounded problem using the policy gradient method, are you assured of converging to the optimal solution? So, so this says that you are solving the multi-bounded problem with policy gradient. So does it always converge to optimal solution? So the answer is no. So, so again we come back to this graph. So policy gradient doesn't give us something that it will always give us the maximum reward. See, over the time it is not going well. It is not always going to give us the optimal result always. It will sometimes give us optimal and sometimes not. Right? So it doesn't give us any guarantee. So the correct answer is option A. We are not assured of any convergence. Okay. So that one was the last one. None of the algorithms seem to guarantee optimality. Correct. None of the option. Still now, what we have done, we nothing gives us any confidence that it will be optimal and converging to optimality. Okay. So that was the last question. So if you have any doubt, you can ask, or we will again meet next week, same time. Thank you for joining. Yeah. Thank you.